Okay, we're going to work through an example or so that would help you to draw a picture when you don't have a picture and apply some of our theorems to solve for the length of a chord that you don't know. Well, you know a few things about, but you don't know what its length is or even part of it. So let's go ahead and start with a picture. I'm going to start with a picture of a circle. Make it big enough that you have enough room. Given information, there is a chord that is 6 centimeters from the center of a circle. So I'm going to go ahead and draw a random chord in here. Draw however you want on your circle. And just make sure you note that that's 6 centimeters from the center of your circle. So I'm going to note that by putting a line, marking the center and putting a line that is perpendicular to the chord to show that I'm measuring from the center. So that length is 6 right there, that green length that I just drew. The chord I don't know the length of, but I know the radius of the circle is 12. So I can do a radius wherever I want. I can say that that's a radius. I can draw out here. I can draw anywhere I want from the center to the outside, but I'm going to say, let's draw a radius that's going to help us. So I'm going to draw a radius from the center to one of my points of my chord, one of my end points. Okay, another good choice would have been to draw right here, but I really don't need both of them. That's a length of 12. And what I did is I just set myself up a perfect problem where I actually have a strategy for finding the unknown length, which is the length of the chord. Now, let's not jump ahead of ourselves yet. I'm going to say that we're actually going to solve for one of those pieces right here. Oops. One of these parts of the chord, I'm going to call that x. And then recall that we have a theorem that says that if we have a radius, because this is really a radius, it's just not continued all the way, but I could continue that, and that radius is perpendicular to the chord, then I know that the two parts are going to be equal to each other. So really I also have an x over here. So going over here, I'm going to say x squared plus 6 squared is equal to 12 squared, and apply my Pythagorean theorem, giving me x squared is equal to 108, x is equal to the square root of 108, 36 times 3, that's giving me 6 radical 3 for my length of x. But I'm not done yet. The question actually asks to find the length of the chord, and note that the chord, the original chord I was trying to find, is actually 2 times the length of x. So I'm now going to say that my chord is equal to 2 times 6 radical 3, giving me altogether 12 radical 3 centimeters, I believe, is what the units were. Okay. That problem can have some variations, just so you know. It can have the variations of, you know, the length of the chord, but you're trying to find the distance it is from the center of the circle. It basically always comes down to the same triangle, that right triangle that we've got going on right here, and you're just finding one of those 3 pieces. You could also be asked to find the size of the circle and find the radius. Okay? One other variation that's a little bit harder is, let's take a look at number 7. Number 7, we are trying to find the diameter of a sphere. So we're taking that problem basically to 3 dimensions. Let me show you what I mean by that. Okay, I'm going to try to freehand this one in terms of the drawing so that I can get a 3-dimensional picture, not just a flat circle. So we've got a sphere that we're looking at. So again, pardon my picture. Well, this is my attempt to kind of show you. Whoops. So I've got a plane slicing through the center of the, 8 centimeters from the center of the sphere. Now, this isn't the kind of plane that you fly in. This is the kind of plane that we talked about at the beginning of the year in geometry class that would be a flat surface, extends forever in all directions, but can never bend or turn. So the plane is going to be perpendicular to the distance measurement, which I've just drawn in green there. That 8 is the same as my 6 was up here, as in distance from the center of the circle to the chord. Now it's distance to a plane, but that plane is going to function like my chord, because basically it's going to make, where it cuts off my circle, it's going to make a circle of intersection, but if you're looking at the side view, it's really just going to look like a line. Okay? So that line, or that circle of intersection, is going to have a radius that's right here. And that diameter, I'm sorry, we know the diameter is 20 centimeters. So that would be all the way across that circle. I'm going to know that this is 10 right here, that radius of that circle of intersection. Find the diameter of the sphere. So the diameter of the sphere I don't know, but I'm going to propose that if I can make a triangle right here, I'm seeing a right triangle, then I could find the radius of the sphere, and then if I find the radius of the sphere, I can actually find the diameter by doubling. So there's your picture to start off. Why don't you go ahead and see what you can do with Pythagorean theorem, and then see if you can actually get the entire diameter of the sphere when you're finished. Okay? A quick tip on number 8. Number 8 is going to be a similar concept, except number 8, you're trying to find the measure of the arc cut off by a chord. So remember that arcs are equal to angle measures, central angle measures. And then my other hint to you would be to remember everything that we can do when we have a right triangle. We've got multiple methods. So use your tools and see what you can do to find an angle measure. Pythagorean theorem works great for side lengths, but isn't going to work for angle measures. So you're going to have to be creative and see what you can do with that. Good luck.